Is there any symmetry that we can exploit to do less work? Because the way that you do these things is, if you're asked in a test, you assume there's symmetry, you compute the components that you know you have to work out, you say the others are 0, you finish the test, you come back and you check. You do the other testicles. Right, so let's have a look. Over here, we say that the density is radially, linearly changing with radius. Okay, does that affect the symmetry around the x and the y axis that we used to have? Does that change the symmetry that we used to have? Who says it does change it and we now have to compute more inputs? Who says definitely doesn't change it? I'm confident that the x and y integral will be 0. Alright. You brave travelers, you are right. So let's think about the symmetry. Let's try and drill the symmetry problem. If you look at the circle from above, right? It's the distance from the radius that matters. So if this is some slice, some horizontal slice, looked at from above, the distance that matters over here and over here, the radius, the distance to the center, is the same. Let's in fact make sure that they are in fact diametrically opposite. Right. So this piece pulls the center of mass that way. This piece pulls the center of mass that way. They both have the exact same mass because the mass distribution is still symmetric about x and y. So, when I add them up, they'll be pulled that way and back again. And they'll be right in the middle. Here's a question. Can you make that argument a bit more formal? Can you convince yourself with more certainty? Physicists generally are happy with that kind of thing. They'll draw a circle with 2 stars in it, and then they'll be happy. It's symmetric. You can see it's symmetric. It's intuitive. The question is, can you come up with something? As mathematicians, can you make it formal? Well, the most formal way obviously is to do. That seems like a bit too much work. Is there another trick that you can employ? So, what you can try doing is you can try considering what happens to the density when we replace x with minus x. Right? And what happens to the density when we replace y with minus y? And let me just be, for completeness, to make sure that I'm not talking absolute bogus to you, when I replace z with minus z. So, when I replace x with minus x, is the density the same? Well, if the density were uniform, it certainly would be, because for every x that's inside the hemisphere, so is minus x. The density is not uniform, it's radially dependent. How do I determine what the density is at x and at minus x? So at x, y, z, there's a point, and at minus x, y, z, there's a point. Right? What's the density here? Well, it's dependent on the radius. What's the radius? The radius is none other than the square root of x squared plus y squared plus z squared. So rho is a function of x squared plus y squared plus z squared. And over here, rho is a function of minus x squared plus y squared plus z squared. Okay. Is there any difference? No, because minus x squared is x squared. So the density at these 2 points is the same. What about this transformation? transformation. If I replace y with minus y, what happens to the density? It's the same, by the same reasoning. Okay. That's great, x and y symmetry. But we're pretty sure there isn't z symmetry, or the center of mass which is the infinite. What happens when I replace z with minus z?
Because you have a heavy sphere, you don't have negative side, it's just positive side.
Exactly. The density below the axis here is zero. Because there's no hemisphere there. Right? The hemisphere is only on top. So when you go up, you have a piece of mass here at x, y, z. But when you go down and reflect it at x, y, minus z, there simply is no mass. So the density is zero below, whereas the density is something above. So there's no symmetry here, so these two symmetries hold. Right, this is what I've done here is the mathematical treatment of symmetry. It's very, very often that someone will talk to you, particularly physicists, they're very guilty of this. They'll say, it's symmetric. So we can neglect it. Or it's symmetric, the symmetry says this. And then physicists later on become very obsessed with symmetry. They even have a theory that they call supersymmetry. It's just super. In fact, you know, symmetry is very central to physics. It's central to a lot of things. In fact, the study of differential equations, the study of many different branches of mathematics. Group theory, in fact, can be called the language of symmetry. And what you should bear in mind, wherever there's a symmetry, there's a transformation happening. Symmetry and transformations are intricately linked. And I suppose I may as well say that now. Wherever there's a symmetry, there's a transformation. If there is a symmetry of, if there is symmetry in the x-axis here of this density distribution, what do you ask? You ask, under the transformation that changes x to minus x, does anything change? And if it doesn't, that's a symmetry. When you want to know if there's a symmetry in the y-axis, you ask the question, well, the transformation here is y to minus y. Does anything change? No, it doesn't. Behind every symmetry is a transformation. Think about looking in the mirror. You say, oh, mirror symmetry. Everything looks the same over there. Well, that's simply the transformation called reflection. You take what's on this side and you reflect it into this side. And if the object under that transformation remains the same, it's symmetric. And so I can give Richard Feynman's most famous definition of symmetry. He said, something is symmetric if I can do something to it, and after I'm finished, it looks exactly the same as it did before. Something is symmetric if I can do something to it, and after I'm finished, it looks exactly the same as I did before. Now, let's have a look. Let's consider this book. Let's consider this book like this. Rotation through 180 degrees. I'm doing something to it. Let's ignore the red stripe on the side. Let's assume it's just a black book. As I rotate through 180 degrees, if there was no color, it would look exactly the same. Even though I changed it, but after I was done, it looked exactly the same as it did before. Behind every symmetry, there's a transformation. Symmetry is invariance under transformation. Right, so now that we've mathematically bashed symmetry with a mallet and cracked it open, we can start reasoning about symmetries in this more formal way. Right, so that gives us some further confidence, although the ultimate proof is of course in the pudding, and we would have to really just work on the integrals and argue about the oddness or evenness of the functions in order to really show that these are zero, but this symmetry argument is quite convincing. It says there's as much mass pulling it that way as there is pulling it this way, in the x and the y directions. So the x and the y integrals, they must be zero. The z integral, however, that is not true. So we must work out the z component. Let's do that. The z center of mass. 1 over m integral of z dm. When I write out something like this, I now proceed to unpack it in the exact same way that I unpacked the one upstairs. That's why that's always the first one you do. Because we'll do the exact same thing. The hemisphere hasn't changed shape. It still looks like a hemisphere. It'll still have a good parameterization of spherical coordinates. It'll still be a good plan to use this range of all these parameters. And so, it'll be a good idea to do the exact same thing that we did before. This is 1 over m. The integral becomes integral 0 to r, integral 0 to pi by 2, integral 0 to pi. We still have rho of r dv. That's still what dm looks like. There's just one extra thing, z. So it's going to be z times by rho of r dv. And dv we may as well write out as r squared sine theta d5 dr. Right. So what do we write for z? R cos phi. It's simply the z coordinate in spherical coordinates. So we look at our transformation equations, which, if we are in an exam, we've made a table with things like the transformation equations so that we don't have to study. And we open our page on the little bookmark which says spherical coordinates transformation equations, and there they are. The z component says theta for us. Yes. Right. So we now evaluate this integral exactly as mundane as before. The only thing now is rho r. Rho of r is simply 3 times r, as decided there. But what is c? We worked it out. C is this is the half pi cr to the 4. So, well, let's keep it as c for now. We'll substitute it as cr. Right, so there's an r here, and 2 r's there. That's a large number of r's. Ultimately, we're going to have c over m. 2 pi, and then we'll put a 2 pi down. Integral naught to r. Integral naught to pi by 2. R to the 4. Constant term. The theta dr. Sine theta. Cos theta, sine theta. We can normally write cos theta, sine theta in another way. We can normally write that as a half sine theta. Cancel. So, somebody gives me an answer. I'll wait for a... In the meantime, I'll simplify the stuff at the front. C is 2m over pi r to the 4. So I can replace it over here with 2m over pi r to the 4. And I'll get 2 over r to the 4. term. Okay, so the final answer then is 2/5 of the way up. So what happened? What was it before? What was it for a uniform hemisphere? Anyone remember the answer? 3/8. So what's bigger, 3/8 or 2/5?
What? Same P. 2 pi over 2
Bigger, 3/8 or 2/5?
Same pi.
Bigger. I would say quite a many.
No, mola vuol dire che tu cose, che vogliono per tu cose.
Okay, well, we can compare it, right?
You took the easy way out.
What does that tell you? It tells you that the center of mass of this radially distributed hemisphere is higher up than it was for a normal hemisphere, for a uniform one. Does that make sense? Most of the mass is at the edges, so you think the center of mass will pull upwards. Which is why you may as well think that the center of mass of this guy is bigger than what's before. In fact, if you've got a smaller answer, you may want to question your words. Right, that kind of question is a good question to ask. After doing this exercise, could you have guessed in advance which one was bigger and why? Maybe I should write that down. Right, let's take some math. Yes.
Did you say that the term was bigger because the center of mass is along the boundary of the corpus?
Yes, because the mass is distributed radially. What does that mean? The mass being distributed radially means that it's very light at the core of the sphere. And it gets heavier and heavier and heavier as we get further out. Think about those, did you ever eat those Astros? Those sweets, Astros. They've got wafer in the middle and chocolate on the outside and candy on the further on the chocolate, right? So you can imagine a very light thing like wafer at the middle, a medium thing like chocolate, and then candy. So your Astro is a good example of a radially distributed density. Now, if you think about that thing carefully, what you're going to see is that most of the mass is on the edge. Most of the mass is in the shell. And so you can imagine that the center of mass is further outwards and not so close to the center. Of course, if I asked you the same problem, but I said it's not a hemisphere, it's a sphere, what would your answer be? Where's the center of mass? Middle. Because this cross becomes a tick. Okay. Any other question related to this one?
How would you know if it was the opposite way? Rather than the mass going outwards, going inwards?
So you mean like exactly what?
How would you know?
C times 50 look like this. guy is very light on the outside and very heavy on the inside. I can't think of an example of this one, maybe here. Gas giant. Gas giant. Yeah. So it's big stars, right? Where most of the dense metal, the dense material falls towards the center of it, like the sun. Very dense in the middle, very light at the edge. Like most things in space. Okay, so if there was an R squared here, everything would be exactly the same. All that changes, that would become an R squared. So you get a different answer here. And when you're doing it over here, you have an R squared here as well. And everything else would be exactly the same. Just over here. Okay, can anybody answer that question for me? If I just chose the lower hemisphere, what would be the center of mass? Would just be negative, right? Because a hemisphere is a hemisphere. No matter how I move it or where I move it, the center of mass is always 2/5 up from the center, up along the central axis. So if I move it sideways, the center of mass is still there. If I move it upside down, the center of mass is still in the same place. Yeah. It will always be 2/5 of the way towards it. So if I put an hemisphere here, center of mass is here. If I rotate it upside down, the center of mass same distance on the same point. If I move it in any arbitrary orientation, center of mass at the same place. Make sense? Center of mass is defined relative to the hemisphere itself, but it will always be in the same place on the hemisphere. Just because I put the hemisphere upside down, the center of mass is not going to move. It's going to be in the same place inside the hemisphere. For a sphere, the center of mass is the same. Any hemisphere if you take the lower hemisphere, the center of mass will be this same down. The upper hemisphere was up. Whoa, guys! Whoa, easy there! You always have the option to, take your conversations and your mouth. So, electric stars do a lot of things. There's equations. If you're studying electric stars, look up the name in the equation. It's the equation that governs the behavior of stellar explosions. Center of mass of any spherically distributed thing is in the middle.
If you don't mind, can you please do that trapezoid question from the R?
Okay, there's a little glitch there, right? Because what I told you was a tetrahedron. And then what I told you it was called is a trapezoid. So some of you went to look at trapezoids on the internet and got the right answer for a trapezoid, which is not right. And some of you did it for a tetrahedron, calling it a trapezoid, which also got right. The center of mass of the tetrahedron is just the center of mass of the vertices, which is very easy. The center of mass of a trapezoid is not so hard either. And I don't think I got the question wrong. Right, so I don't really think it's necessary to present that Safe, you can be safely assured that one comes. Any other questions related to touch questions you tried? Good, we're gonna close it. So what touch? Okay, let me make that formal. In this touch book, everything detailing single particle Lagrange mechanics is neutral for touch. Everything involving single particle and then touch 60 is working on moments of inertia. That's important. Everything including the laminar theory. Now we're getting into the territory that's not as important. Stuff like touch 19 and 20 and let's not focus too much on 19 and 20. 21. 22, try 22. It'll be something very similar. And try 24. Which unfortunately is almost printed. So everything up to 15. 16, no, everything up to 16, very important. Those next ones are not that important, but make sure that you are comfortable with touch 22 and touch 24. Make sure okay, I'll make this form. The moment of inertia tensor will not be in the class. Up to there.